are going to talk about algorithm techniques in general. So although I'll be taking a few specific algorithms, but we'll also be categorizing them. So we'll say this is that style of algorithm development, and the other one is the other style of algorithm development. So the first one is something that we have seen lots of times already, binary tree style, reduction. So reduction is a binary tree, complete binary tree. Sometimes we say balanced binary tree. Sometimes we say algorithmic technique. And it's essentially a tree. This is a logical tree, right? A tree of computations. And you can imagine having data at the leaves with every node performing some computation. And for this description, we are not focusing on whether it's OpenMP style or MPI style or any other style. It's just parallel threads that may be on the same machine, may be sharing some memory, may not be sharing memory, may be communicating somehow. But this is at a higher level of logic. At every level, you get some information, some output of the computation from your children. You perform some more computation on it and produce an output for your parent. Okay? And when this reaches up to the level of the root, then the computation end result of the computation of the root is the final result. You can also reverse it. You can say root does something, then it provides some input to its children. They do further processing on it, provide some more input to their children, and the output at the leaves together is the output of the system. Okay. Anything that maps to this style will typically have log n steps of whatever size. Right? So assuming that each node is doing order 1 computation, and you can change order 1 to anything, there are log n of order 1 computations. Right? Because until the bottommost level has done its work, the next level can't begin. And all of that can be done in parallel. But the next one can't be done in parallel with the previous level. And so after 1 unit of time, the next level of nodes activate. Then after 1 further unit of time, the next level activates. And after log n unit of time, the root has activated. Or vice versa. Total time is order log n, and total work will be order n. Right? Assuming again order n times whatever the individual computation is. So if everybody is doing order 1, taking order 1 amount of work to do, then total amount of work will be n. Right? And the remaining question remains is, of course, this is you're using order n nodes to process order n things or to produce order n things. In fact, 2n nodes, right, to process n things. And you'll probably have only p processors, not twice the size of the input. And so what would be a good way, or what would be a way to map these to the p processors? Okay, so similar to work scheduling that we talked about earlier, what would you need to do? How? What does work scheduling say? What should you be doing? Everything that is done in a unit step is distributed to all the processors available. So every level is going to be distributed to p processors. And at some point, the number of nodes is going to become smaller than p. And then some processors will be idle. Okay. So something like this. You have processors 0, 1, 2, 3, 4, 5, 6, 7 performing the leaf level, leaf node, so to speak, computations. And then in this particular case, 0, 2, 4 onwards are doing the next level, you could have said 0, 1, 2, 3, half of them are going to do. Then at the next level, half of them are going to do, right? And so once the number of processors becomes bigger than the size of your the width of your tree, then some processors will remain idle, and you figure out which you want to use, which you don't. Okay. In some situations, it would make sense to use specific ones. We'll look at such a situation very shortly. And so,
even in this kind of thing, there are many possibilities, right?
Yes.
There may be one job where your the data size that each processor is working on keeps constant. For example, if you are adding n numbers, then each processor has to take only 2 numbers.
Yes.
Or you may be doing something like sorting, where you each processor has to merge the result of its child, where the size keeps growing and growing. Can we do those two, even those two or other different?
Using a tree scheme, right? So,
the analysis of can all those be analyzed together?
You wouldn't want to necessarily, okay? So this is because of the kind of widespread use of reduction in pretty much, or some flavor of reduction in pretty much every parallel algorithm you will come across. There will be a tree somewhere along the way, okay? But this is saying that tree is basically your entire computation, okay? So again, this is a point I have made before. When we categorize things, it's not just to say that you have a problem and then you're going to say whether this category of algorithm would suit this problem or that category. It's more like these are the different ways in which I can process the input, see where I can combine what. Okay, so it's not necessarily that clean of a decision to make. Okay, all right. So in this case, I'm showing an example where at the leaf level, you have more processors. So 0, 0, 1, 1, 2, 2. And then next level has only 4 processors, 4 nodes. So you get 0, 1, 2, 3. And then you start skipping that. Okay, you had a question.
So, in this tree area of implementation, for example, if you implement like an MPI thing, so what actually happens is the way you write a code, so the code is running all the 8 processors, but as it goes on, like by 2, I mean n by 2 keeps on reducing, and but still there will be something running on those processors based off time, right?
Yes.
And that cannot be avoided.
It can be, right? So in this case, if there is, for example, let's say to take that example, we are summing things, okay. All right? And you are basically taking 2 things, adding, producing a result, and that's all each node does. Then all those extra processors at the top level are not going to buy you anything. Right? You can do nothing with it.
But the way we write MPI, like literally there are 8 processes running, and as the time goes, remaining 4 are still running, because finalize is like the way everybody joins back and comes out, right?
Right.
That means they are still there. We cannot actually kill them off.
But if they are doing nothing, are they costing you anything?
But there will be some setup running there. I mean, they will be costing.
Yeah, they eat up one processor for some reason.
They will be eating up
do something.
100%?
Not 100%. I'm not sure.
They don't.
Not 100%. At least in the graph, so it takes a sample.
Yes, it keeps doing some work, right? But it's one of the nodes on which you're doing nothing probably. And so at least somebody else is slowing down because you are running some small load. MPI, there is no reason for that particular restriction to be universal. Right? There's no reason that MPI had to implement it that way. It's just easier to do certain things when uniformly. And so, but I think that that's a small overhead that is not worth worrying too much about. Okay. All right. So now, thinking back in the terms of dependency graphs and all that, given that this is the computation, we are going to have to worry about when a given node is ready. Right? When does it start its computation? So who are the predecessors in the dependence graph. Okay, and that forms what is known as a binomial tree among all the processors that are available. Okay, we're not going to go into the details of dependency graph analysis here, but just as a piece of information, it's something useful to know. A binomial tree is a tree where the number of children keeps growing as you go up the tree. So recursive definition of binomial tree is that if you have a single node, it's a binomial tree. Okay? We call it B0. Typically, single node binomial trees are just the roots. And BK is a tree which has a root with K binomial trees as its children. Okay, so B1 is a root with one binomial tree as its child, which is B0. And B0 is single node. Okay. And similarly, so take an example. That's B0. That's B1. Right? B1 has a root with B0 as its child. And this is B2, which is a root with B0 and B1 as its children. And that's a root with B0, B1, and B2 as its children. Right? So how is it related to the dependency? If you go back and look at exactly, the top 0 depends on 2 and its children as well as its children on its side. Okay, so if you expand this out, you're going to get exactly this binomial tree. Okay, so now let's talk about a somewhat non-trivial or non-obvious, let's say, algorithm that uses this tree. Reduction is one, right? We've looked at that. Prefix sum was the other thing that I had mentioned, and we're going to talk about that as the next algorithm. So this is the definition of prefix sum, just to repeat, and I'll leave that up there in the corner. We've got a set of numbers, and this is written in a PRAM style. You can port it to OpenMP, MPI, whatever you wish. X is where it's an array where the input is given to you, and P is an array that you're producing which contains the prefix sum. All right. So for the first element of the resulting array is the first element of the input array. P0 is X0, and P1 onwards is the sum of all the elements in X before that. Okay, so P7 is the sum of X0 to X7, and P10 is sum of X0 to X10. Okay, how would you compute it efficiently? So if you look at the dependence tree, it is very clear that each computation depends on the previous computation, as this loop has been written out, which means you're going to have to repeat something, replicate something, so that this can be done in parallel somewhere else. And if we can map it to the binary tree style computation algorithm, then we can expect that it's going to be done in log n time with order n work.
We can model it as the way we do parallel sum. We can first store the consecutive number sums, and then we have an array of sums. Then do it incrementally.
If you do it incrementally like it's written here, then it's going to take n steps, isn't it? Then how incrementally?
Same element can be summation can be computed by all the nodes, but then some process stops and
another element then broadcasted to other set of which uses the previous sum and this new element.
Okay.
And again some element.
When you do broadcast, you have to eventually think of the cost also. Right? If it is a shared memory model where everybody can read, you write somewhere, everybody can read, then maybe it's okay. But in other models, it can be expensive. But again, complete your algorithm. So assuming broadcast, what do you do?
So like x0 is given to the root node, then x1 will be given to the another level of nodes, so which will do the summation of previous node and plus the new element. All the nodes will do the summation. Then again some set of processor will stop, like half of them. Then the x2 will be given to other set of processors which will do the sum of their parent plus the new element. All the nodes will do the summation of the parent plus the new element.
But where did the parent get the sum from?
Basically, in the previous step, the parent basically has done the summation of the root of their parent plus the new element.
So parent is summing one element at a time?
Like you will get the x0.
Yes.
Then in the other level, x1 will be given to both the nodes. So what they will do, they will pick up the sum from their parent plus the new.
So both of them will do x0 plus x1. Okay. What will the children do?
Then whatever their parent has computed.
Both have computed the same thing, x0 plus x1.
So the half will stop now. X0 will stop now. X1 plus the parent sum will be computed at the next level.
No. So there are two nodes, both have x0 plus x1. And you're saying one of the node will idle itself now. And so now basically we have one node with x0 plus x1. And its two children will do what?
So the graph will almost be similar to the binomial tree.
Okay, but what will the other two children do of the node that has x0 plus x1?
So it's basically like n by 2. The way it's become like 3, 4, 6, 4. That's how the way.
That's what I want to get to.
Starting from the bottom to up, at each node I can keep the sum of the left subtree. So that will take me order log n when I have n processors. Then starting from the top, I will send that data to my right child, to both the child. And if it is a left child, it will keep that value. If it is I will send it to the right child, and it will add its value to it. Then it will send it to its left child and right child. At the when I reach the leaf, I will have the sum of the previous elements, and then I can add them.
You have the right approach, but it's not fully formed.
Coming down.
So let's look at this algorithm for trial. It's recursive, and I've drawn the leaf level here. And you can enroll the recursion and do other things, but I'm not going to physically enroll the recursion here. At the leaf nodes, you take those two elements, add them together. Okay, so I've got n by 2 sums. Each is a sum of pair. So first is 0 plus 1, second is 2 plus 3, and so on. Now I recursively say compute prefix sum on this. Okay. So I've got the prefix sum of that n by 2 set. But I really needed the prefix sum of this n set. Can I get from that sum to these prefix sums? So these prefix sums of the circles you are seeing here, the leaf nodes, are exactly the prefix sum of the even ones, right? So if that guy wants to know its prefix sum, it is just what the parent says. Okay. So if you number from 0 to 0, 1, 2, 3, then this is odd. Okay, right child has the same prefix sum as the parent. What about the left child? Parent has also added its right child, right? So parent minus the right sibling, or the parent sibling plus itself. Okay, so it's given that plus is the operation, right? We said we've a function that does the reduce operation. So although I'm using plus as an example, it can be any left associative operation, okay, which user can even define. So it may not always be invertible, but if it is invertible, you could do both of them. If it is not invertible, you can at least do one of them. So this is the final algorithm. Okay, this is written in, again, PRAM style. So everybody shares memory, shares X and P. So for all the elements, you take the pairwise, here it's written as sum operation, right? We're talking about sum in the previous case. You perform that operation on X twice I and twice I plus 1. Right? So 0 will do 0 and 1, 1 will do 2 and 3, and so on. So that gives you the first level. And then you call recursively prefix sum on that new set Y and get Z, in which the prefix sum is stored. And then reinitialize the output. Now we are generating the final output P. 0th element is always x0. So we'll initialize the leftmost value of the prefix sum. And then we'll do what we just talked about, right? If I is odd, then whatever your parent says, whatever that square leaf node's parent says, is your prefix sum. So P of I is Z, which was the return from the recursive call of your parent. Otherwise, it is your parent's left sibling operated with you, added to you. Okay, and if it is invertible, then you can apply the inverse of that operation with your right sibling also. How long does this take? Log n time. And work? And log n. Problem with recursion is that it is hard to do the scheduling, right? Because you can't clearly see it, but it can be done. And so let's unroll the recursion and then try to schedule it ourselves. Before we do that, talking in PRAM terminology, is it what? EREW, CRCW, what kind of memory model are we using here? Are there any concurrent writes?
No, concurrent reads, exclusive.
Are there concurrent reads?
Concurrent reads are there. Two siblings are trying to read their parents' data.
Not their parents' data.
The parents' siblings. So
Parent sibling, right? Somebody is reading the parents' data.
At the lower level.
Right.
At lower level.
How many?
Two.
2. Can you get rid of the concurrent read? Actually, it already has the getting rid of the concurrent read. If you are the left sibling, then you will read your parent. So in that if left, everybody is unique, and then in else, everybody is unique. Right? So actually it is exclusive read and exclusive write.
In the PRAM model.
In the PRAM model, right? And so you can very easily extend it to MPI model and whatever else, because there is no reason for two people to read the same thing. Okay, so now let's unroll it.
How do we get the parent siblings data?
It is MPI.
You just have to find the address. Right? If somehow you have done the mapping, so you have to know where the parent sibling is. In fact, it wouldn't necessarily be just the node number because you'll have many fewer processes. But so you have done the mapping, so you should know where it is. Okay, let us look at the tree version, right? Unroll the recursion. And so in the first pass of the tree, going from bottom to up, suppose we create all the sums. Okay, we are storing the sum in each of the nodes. And now what I would like to do, and by the way, there will be the terminology that I'm using here is S bracket close bracket 0 to n over 2 means that it's storing the sum from 0 all the way up to n by 2, whatever is just before n by 2. N by 2 is open and 0 is closed. And similarly on the right child of the root is giving it S n by 2 to n. And similarly the left child of the right child of the root is giving it S from n by 2 to 3n by 4 and so on. Okay. So now everybody has these sums. So I have the sum of everything, I have the sum of the left half, sum of the right half, sum of the left left, left right, right left, right right, and so on. How does this help us to get the prefix? Suppose now we start to go from top to bottom. Okay. We have stored. So typically in your regular sum, what would you do? You will say S equal to S of some left child and S of right child, and one of you are holding one of the left childs, one of the children, right? If you remember the mapping, right? Every level is mapped independently with each other, and so say the level below you is 0, 1, 2, 3, then 0 will get 0 and 1, 2 will get 2 and 3, right? So 2 is holding 2. When I say 2 will get 2 and 3, it's going to add to its S the result of 3's S. Right? So its previous S is gone. You're reusing the same variable. But now we need to store it. We need to remember. So for example, root was also involved in the leaf level computation. So root needs to store the full sum. It also needs to store what happened when you added 0 and 1. And it also needs to store what happened when you added 0, 1, 2 and 3. Right, at the next level, and so on. So now, what do we have at the root? Is a prefix sum of everybody. How will the root's two children compute the prefix sum of the left half and the right half? What is the prefix sum of the left half? Whatever that fellow had computed earlier, right? Which is still it's the same thing, same root, the same mapping that we had used earlier. So it is there. What about the right child? Root minus left sibling. Would you want to do that? I don't even know whether minus exists. I don't want to go in the direction of minus. Can you do with just plus? In fact, that the what is coming down the arrow is being shown.
What do you want?
You want prefix sum of the left half and the right half, right? So from there we'll generate, if your parents have the prefix sums, can you generate the children's prefix sums? We'll start at the same slide. We were trying to work out the prefix sums.
So just a question, in the root, the top root, it is storing from 0 to n or 0 to n by 2?
0 to n, right? So the previous picture that you had seen, which is now beyond this, is what is being sent on the two paths for the root to compute the sum of. And so the root has the sum from 0 to n, and it also has the sum from 0 to n by 2 because of the previous case. So it can send the data that it needs to send. So you can think of it as the following. To your left child, you send your sum. The sum that the parent is giving you, right? Whatever the sum that the parent computed for you. But to the right child, you're going to send your left child's data. So what is that doing?
So the left child will add its own value and the data it receives from its parent to get its.
So if you're basically doing the same thing that in the previous case, right? If you are the left child, what do you have to do? To take the parent's left sibling, right, and get that added to you. So you know your value, so you can add that later, but you have to get the parent's left sibling. How do you get that?
At the first level on the right child, what data do you want?
First level meaning from the top. Yeah.
What do we want? What sum do we want?
For the time being, we are not the input problem. Right? Our intermediate problems we can figure out, but we'll figure out from this that at the leaves we want the prefix sum at the end.
So you're doing this. You have computed all the heads. From there, you're generating all the prefix sum in the reverse order.
Yes. So because I want all the prefix sum of each level, right? So for the recursive operation, what had we done? We had said, if you want to compute prefix sum of this level, you reduce your set, compute the prefix sum of that level, and then either take your parent or take the sibling.
In that case, we need the left value for computing a prefix sum in the right side.
Yes.
That's the reason you're passing on that. But left side doesn't need the right value because it's
left side does not need the right value. Only the right side needs the left value. Right. So now with that, what do you expect? What data should you expect at any level? At the first level, for example. First level should, at the end of its business, have the prefix sum of the two values that came to that at the first pass. Meaning that the left child needs to have 0 to n by 2 and the right child has n by 2 to n, right? And left gets the prefix sum of that, meaning only 0 to n by 2. Right child gets prefix sum of these two things, means the sum of everything. 0 to n. Right? So right child gets what the parent gives it because parent had 0 to n. Right? And left child already had it, yes, already had it. But just to keep it separate, we're going to get it into, so for example, suppose we are generating this in an array, then we'll copy it from somewhere else in that array. Okay. So just to write that out.
So in each level, the left child will pass on the value to the right child sibling. I mean, that's the other side will happen. Or the parent is passed on.
So now that we are going back to the shared memory PRAM model, we're not going to say that this process is passing somebody to that process, right? Whoever needs it will figure out where to read it from. Right? So if you either read it from your parent or the sibling. Okay, so that's what's happening here. So you begin and the data is in array called A. So for some reason X has morphed into A because I said A, B and C. A is the input and for all the input data, you're going to put it in B. Okay, 0th level of B. So B is computation of the sum in the upward direction. C is in the downward direction. B is going to contain the sums, partial sums. C is going to contain the prefix sums. All right. So we begin by the 0th level B. So B is a 2D array. Why is it a 2D array? Because we need to store. We can't simply say S is equal to S plus the other child, because we need to store all the partial sums that everybody has seen. And so B will store the partial sums of different levels in B0, B1, B2, B3. Okay. And the second dimension is how many elements there are on that level. Okay. So B0 will have n data, n elements, which will come from the input set A. B1 will have half of them, which will come from pairwise sums of B0. B2 will have 1/4 of the input sum, which will come from pairwise sums of B1, and so on, right? So after we have initialized by copying everything to B, so after the first loop, which is parallel for setting of A values into B0 rather, then you go for log n levels, right? From the bottommost level to the topmost level. And so for H, which is the height, you go starting from 1 to log n, you do in parallel stuff for each level. And so parallel for every H value, and I goes from 0 to n by 2 to the H, because it keeps reducing, I keeps reducing. And as I said, you compute BHI from BH minus 1i. Okay, just take pairwise sums. And at the end of that, the second bullet item, you've got the sums after you've done all the log n levels. And now, down from log n height all the way top to 0, you initialize the prefix sum is now C. And so you copy the prefix sum from B to C for the top element, right? Which was at the top there is only 0, so you've just copied into C. And now, as you go down level, for every level, what do? If you are the left sibling or right sibling, you do different things. If you're the left sibling, which means I is even, then you're going to take the siblings, your parent siblings prefix sum computed so far, C, add to it your value, your partial sum, which is B. And if you are the right child, then you simply take your parent C, because your prefix sum is what your parent computed. Okay. So you're basically doing the same thing that was earlier shown for the recursive procedure for just the bottom level. Now you're doing this at every level. Okay. So you've basically unrolled the recursion, and now it's very clear what the time and the work complexities are. How much time? Log n, right? You go in parallel, log n steps, and then log n steps coming down. How much time for each one of these steps? Everything is being done in parallel. Okay. Similarly, work will be n, because you're doing order 1 work at each node of the tree. You go once up, once down. Okay. And so this diagram shows the data flow of how B values, B got initialized for 0 from A, and then you got the sums, partial sums, as you go up to B1, B2, and B3. And then C at the root got the B value initialized, and then you keep coming down. And the way you keep coming down is being shown by arrows in this diagram. Okay, so if you are confused, then you can go back and look at this diagram and get yourself reoriented. Order n work, order log n time. Processor mapping, does it make a difference? How we map each level? Suppose I say 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5. So let's take an example. Suppose we have two processors. And instead of this mapping, in this mapping, P0 is taking the left half, P1 is taking the right half. Suppose I said P0, P1, P0, P1, P0, P1, if that were the mapping. Would it be any different in certain situations from this mapping?
Every left child is P0 and every right child is P1. That's what you mean.
Yes. If we said P0, P1, P0, P1, then every left child would be P0 and every right child will be P1. How does...
Less data IO taking place, less communication taking place between processors in this model.
So if we consider that
You read exactly the same amount, right, from the memory. Assuming shared memory, right? You're talking about if it is...
The sharing is the same, but
and
it's,
this so it's PI.
The processor will be working on equal that just like the level next to the root level till that time both are busy. Say in this case I can say that if P0 is busy and P1 finishes earlier, so P1 is idle. In that case I think both will be working.
Right, so at each level you'll have two pieces of data from two different processors coming and joining at up to a certain level. Also, if you've got a SIMD-like environment, right? So this is if everybody is even going to one processor and everybody is odd going to the other processor and both the processors must do the same thing in a given clock cycle, then you can't because they want to do different things. At every instruction, this guy wants to say do X and this guy wants to say do Y, which means every instruction is going to get broken into two instructions. Once when this guy gets to do its X, and then the next clock when this guy gets to do its Y. Whereas if you do block synchronous as is done in this case, then each one is going to have enough left, enough right to keep them busy, right? So you say, now I'm going to do n number of lefts. That guy also has approximately n number of lefts. And I'm going to now do n number of rights, and that guy also has probably n number of rights. And so every clock cycle, we're going to do useful work. Okay? All right. So in short, balanced tree approach is going to restructure or structure rather the computation into tree-like fashion. And then you're going to traverse the tree up or down. It makes sense to think of the communication as a network topology as all those diagrams are showing, but ultimately it can map to whatever programming paradigm you may be interested in and whatever the number of processors you may be interested in. Okay? We probably shouldn't start on a new topic, but I will anyway, just to get you thinking about this problem, and we'll come back and talk about it on Monday. And this technique is called partitioning. You'll see that it's again going to use some tree-like structure. The idea is that you take a problem, you subdivide it into two problems and solve them. Okay, kind of similar to divide and conquer. Sometimes people differentiate between the two in saying that in divide and conquer, you focus on the conquer part more, and in partitioning, you focus on dividing part more, right? You divide it in the way that then independently the problems will be solved and there would be not much combination to do after the individual sub-problems are done. Okay? Does that remind you of something? Quick sort, right? Merge sort. All right. We are going to do merge sort with partitioning, where we are not going to, well, let me rephrase. We are going to do merging of two sorted sequences using partitioning, where we partition, do the work in the partitioned data, and then we are done. So that's our next algorithm we'll be talking about. We've got two sorted sequences, A and B, and with some P number of processors, we want to merge them, right? And remember, order n is the work complexity we'll be interested in. And what do you guess time complexity we should be interested in? Log-n is a good guess. Actually, you can do much better. Think about how you do it in log-n, and then think about how you do better than log-n. And we'll talk about that on Monday. Okay? Any questions? Okay.
Is there any max
In the reduction? Yeah. It has inbuilt max and min.
See, I just saw only plus minus. What is the keyword? Will you say max?
It has a constant. Yeah, you send it a constant. I think it's OMP max or something. In fact, I had mentioned those keywords in class also, if I recall. It should be on one of your slides. I think OMP max, but I have to check. Okay. I actually mean asymptotically. All right. See you on Monday.